We can consider another example. Suppose the function is a two-dimensional function. How can we find the partial derivative with respect to x and then to y? To solve the problem, we can use the following commands to generate the sample points. First, to create a grid point for x and y, and then find from the original function the value of z. And then we can create a spline using commands like this. Well, it means that for x and y, we both created fixed order B-splines. And from the original data, we can easily create a B-spline function, B-spline object. And for this object, we can easily perform first-order derivatives to x and to y. And then we can use hyphen plot to draw the surface of the result. And now our question is whether this result is correct or not. So this is the result we can finally obtain using numerical methods. So the problem is whether this one is correct or not. Since the original function is given, we can easily perform first-order derivatives, partial derivatives to x and y using commands like this. And then we can easily obtain the surface of the result by the use of easy surface function. We can open another big window. And again, it seems that this one is quite close to the other one. If you compare them, you will see that they are almost the same. So this method works very well. So these are the numerical differentiation problems. We can easily find the problem by the use of Fn. It normally stands for the interpolation, spline interpolation. All the functions started with Fn. Fn well for evaluation of splines, DER for differentiation, for derivatives, and also INT for numerical integration problems. So now let's consider numerical integration problems. We can use FNINT function to perform integration. And it should be noted that we do not have to specify the range of integration because the information is already contained in the S object. If you are establishing the object S, you have already given the information of the interval. So this is a function we use to evaluate the integration of a certain function. So let's consider an example like this. There is a small error here. We do not have to write a pi here. We better use a t instead of pi, because using the numerical integration method, we can obtain a function rather than a simple definite integral. So to solve this problem, we can generate a set of data like this. And as I said again, we only generated 5 data points, which is quite partially distributed. So we can only use 5 points. I've just exaggerated the case where only 5 points are given. 0, 0.4, 1, 2, and only 5 points. And then, how can we find the numerical integration from the data sets? So we can calculate x, y first, and then we can establish a cubic spline object here as T1, and then we can create a B-spline object as ST2. And with the use of these two objects, we can easily perform numerical integrations. And we can find the integration curves rather than a definite integral function. And I will explain this result later to you. Okay, so SP1 is the SP1 is the cubic spline object, and A from this command, A should be the integration curve. So we can use FNPLT A. We can get the integration curve like this. And seeing that this is a cosine function, we should be correct. And I will explain details later to you. Well, I think in the slide, in the command syntax, we may use the argument there as well. So the integration, second order integration, I think we should use 1, 2, like this in the syntax. So this is the integration. If we know fx equals to sine x, then the integration of it should be fx equals to cosine x minus. And this is the integration result. Now let's consider a command like this. Hold on dc plus minus cosine t from 0 to pi. We should use. I will explain that also to you later. You can see that they are different. So why this happens? In this integration, actually the result may not be something like this. It is 1 plus c. So in this case, maybe c equals to 2 rather than this one. So you must be very careful when you use numerical integration. You must consider the value of c as well. If we increase the size, it should be okay. I think it should contain all the information. This one is just a translation of this curve. This one is minus cosine x. And you may have to perform any translation, vertical translation from this curve to get the result. So if you use numerical integration, you better pay attention to the value of c. It may not be always be 0.